In this video, we're going to continue our look into 5.2 by looking at the binomial probability formula. And to illustrate the binomial probability formula, I want you to understand it intuitively. I could put out the formula and you could totally try to understand it and drop numbers in the right place, but I need you to understand where it's coming from. And I'm going to be a little bit better than what they present in the book in terms of the formula itself. So the binomial probability formula will allow us to find probabilities where not everybody is doing the same thing. We have not been able to do this unless we could see the entire sample space like back in 4.1. We have, if you look very closely at 4.2, 4.3, if you look at those, the questions will say this: find the probability that if 5 students are selected from a class, all are males. Find the probability that if we select 10 senators at random, they're all Democrat. Find the probability that somebody has that 10 people are randomly selected from a town. Find the probability that none of them have health insurance. What's happening in all of those is when they have multiple selections, everybody's doing the same thing. And you can say to yourself, well, no, not in 4.3. In 4.3, they did the at least one. Well, think about how we handled at least one. The probability of at least one was handled by 1 minus the probability of none, because none was the exact opposite. That's everybody doing the same thing. We don't want to be able, we want to expand our horizons there. So I'm going to choose something in which you can see the entire, entire space, I guess is what I'd like to say. How about something like this? Find the probability that if a couple has 4 children, exactly 3 are girls. Okay. So I'm trying to do something that we can visualize. So in that process, somebody could say, well, this is easy. I'd go back to 4.1. I'd look at the grid of 8 things that we came up with. I'm going to rely upon that, but only to illustrate the formula. The question that I want to ask you is this situation binomial? Are there a fixed number of trials? Yes, there's 4 children that are being born. Is there only 2 outcomes with each birth? Yes, either a boy or a girl. The way we're keeping track of this, we're focused on girls. So, or better stated, either a girl or not a girl. That would be better stated, either a girl or not a girl. So, a couple has 4 children, exactly 3 are girls, so it definitely meets the first 2 criteria. Probability, the trials are independent. When you have a girl on the first birth, does that make you more or less likely to have a girl on the second? And the answer is no. So what is that probability of getting a girl? Well, boys and girls are equally likely. It's 1/2. So the probability of success is 1/2. The probability of getting a girl is 1/2. Okay, awesome. So what I need you to see is, well, let's talk about having 3 girls. That could be a girl on the first birth, a girl on the second birth. Here's 3 girls and a boy. And so the common mistake is for somebody to say, okay, that's easy. Girl, girl, girl. And then I'm going to put the boy in red, right? Because it's the boy that we don't want. Boy. Right? It's at least not, we want a boy, right? Because we want exactly 3 girls. So that's a little bit of a misstatement, but it's the girls that we're focused on. So I'll leave that in black. This is only one of many situations that are possible. That one single boy could also have been first. And so I'm going to come in here so that there's a measure of consistency. I'm going to put boy in red. Do you agree that the boy could have been the third baby born? And this is one of the reasons why they wanted us to do the outcomes or the sample spaces in the earlier ones, in the earlier sections. Well, that's another one. It could also have been this way. Probability of girl, 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 or one half, one half, one half. I'll try to get faster with this to not waste your time, with the boy being born here. And there's a last option for 3 girls and a boy, and that is, whoops, that is the boy being born first and the 3 girls at the end. So I'm purposely, I chose an example, unfortunately, where everybody has the exact same probability of happening. So that's why I'm putting the boy in red. So what I want you to see every time is that all of the results are the same. All of the results are 2, 4, 8, 16, are 1/16th, 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 1/16th. Every single time the individual calculations are the same, but there are 4 different ways to deal with it. So we got to add up all of these, because either the boy could have been born last, or the boy could have been born second to last, or the boy could have been born second, or the boy could have been born first, right? The other 3 are girls. So we would add all those up, and the probability that you have 3 girls is 4/16 or 1/4. And you've seen that probability before, I think, but we get a nice 1/4 out of that. So let's talk about the formula. The formula is going to look awful in a way. It might be daunting, but I don't want you to memorize it as a formula. I want you to observe something. Here's the formula. Maybe I should show you the formula first. Apologize. I'm hesitating on how best to do this. The probability of x number of successes is equal to c of nx times p to the x times q to the n minus x. Now, if somebody looks at that, they're completely daunted, right? We don't want you to be. Remember our question here. Our question was, find the probability that if a couple has 4 children, exactly 3 are girls. N is the number of successes, right? Or sorry, apologize. N is the number of trials. Let me get to this guy right here. So N is the number of trials. Little p is the probability of success, the probability of getting what you want, a girl, on an individual birth, right? So some people will say, well, I don't know that probability. That's what I'm supposed to be finding out. We're not asking for the probability of 3 girls. We're asking the probability, this little p is the probability that on one birth that the outcome is a girl, and we know that that's 1/2. What Q is, let me describe what Q is. Q is the probability of failure, of not getting a girl in this case. And Q is always 1 minus p. Now, these other things are related to the question. So I'm going to highlight those in red. Whoops, that's not a highlighter. Sorry. This x, and this x is the desired number of successes. So this could be completely overwhelming unless you have a human like me talk to you about it. Now, the first thing I want to ask you about is the question itself. So I'm going to come up to this question, and I'm going to erase the stuff above it, because that's where we're going to do our work right now. And then we'll compare with the work down below. I've covered up the formula. I want to ask you a question. How many children, according to the question, are we having? And you would say 4. Out of the 4, how many do you want to be girls? 3. Oh, you want 3 to be girls. So out of the 4, you want the 3 to be girls. Okay, what's the probability of getting a girl? 1/2. How many times do you want a girl to happen again? Well, I want it to happen 3 times. That means there's some extra stuff. So What's the probability of getting a boy or not a girl? 1/2. And how many times do you need that to happen? I need it to happen actually 1 time. If I'm having 4 children and I need 3 to be a girl, I need 1 not to be a girl. And that's what that thing represents. That's exactly this formula. So somebody might be asking, Jensen, why this? Why this sea of... Sorry, I didn't mean it to be a pen. I meant it to be a highlighter. Why this sea of 4, 3? Calculate for a minute C of 4, 3. Pick up a calculator and type in C of 4, 3 like you were doing in section 4.4. When you do, you'll see C of 4, 3 is equal to 4. Now what's that for? That's the 1, 2, 3, 4 ways that we could get one boy and 3 girls, or 3 girls, right, and 1 boy. It counts that for us. We never have to do that. We don't have to see this space down here. We can rely on this number. Now, why is it times? Because you're getting the exact same number every time. Every time you have 3 1/2s that represent girls and 1 1/2 that represents a boy. Every time. And then you just run this. So let me show you how I would run that in my calculator. I don't have a calculator with me. Must have loaned it out to somebody. I gotta go fix that. But that's actually going to be a problem. So nobody's here that can rescue me really quick. So let's take a look at what this is. We could do this, I think, ourselves actually without the use of a calculator. So P of 3, you're going to first run C of 4, 3 and hit equals, and it's going to produce a 4. Then you're going to hit times 1/2 to the 3rd power. Make sure you use parentheses. So you're going to type in 1 divided by 3 to the 3rd. Well, 1/2 to the 3rd we know is 1/8. So I'm just going to do it that way, times another 1/2. And we're going to get the same 1/4 that we did down below. So that's the power of this. So I don't want to start a new video, but I am going to have to run and grab a calculator. But think about this question, why run and get it? Your final is a 30 question multiple choice exam, where each question has 4 answer choices. And those answer choices, I think, are A, B, C, D, one of which is correct. Okay, so hopefully you understand that. So your final would look like this. 1, a question, and an A answer, a B answer, a C answer, a D answer. 2, a question, an A answer, a B answer, a C answer, and a D answer, right? And they all 30 look exactly like that. So that's what our exam looks like. The question that I have for you is something you've never been able to answer until this point. Things that you could answer are, what's the probability that I randomly guess and get them all right? What's the probability that I randomly guess and get them all wrong? What's the probability that I get at least one right? Right? Those are the questions that we can answer. Here's one that we couldn't so far. If I make random guesses for each question, so I'm not even looking at it, I'm just stating an answer, find the probability that I get 20 correct. Okay, and so get exactly 20 correct. So we have the formula up there. I don't actually want you to rely upon that. I got to be careful how I say that. Yes, use whatever you need in order to do that problem, and I'll model it through that formula, but through talking through it, not through uh, anything more than that, because this formula is super intuitive. That's where it came from, is just intuition. So think about that for a couple minutes while I run and grab a calculator. Okay, hopefully you tried it. I apologize. I had left it and my daughter picked it up and was using it. So, your this question's right here. I'll leave that formula up here, but here, let me ask you some questions. Is this a binomial situation? Yes, we have 30 questions that are being asked. Each question can either be correct or not correct, so there's two outcomes. Um, and then the probability of success each time is the same. I got a 1 out of 4 chance of guessing them correctly. So let's talk ourselves through this. What's the question say? Find the probability of getting 20 correct. So I need 20 correct. No problem. How many questions am I answering? Well, I'm answering 30, of which how many do you want to be correct? 20. What is the probability of being correct? Well, there's a 1 out of 4 probability of being correct. How many times do you want that? So this 1 out of 4 number represents a correct answer. How many correct answers do you want? Well, you want 20. How many wrong answers do you want? Because you definitely want some wrong answers. Well, I want 10 wrong answers then, because I got to answer a total of 30 questions. And so inside here is 1 minus 1/4, right? If the probability of getting it correct is 1/4, the probability of missing it is 3/4. And so if you do it by just pure numbers, n is the number of trials, 30. X is the desired number of successes, 20, gotten from the question. P is the probability of success when you answer a single question, that's 1 out of 4. And Q is always 1 minus that, or 3/4, right? And so that's where that's coming from. But I just love for you to be able to say, hey, I'm answering 30 questions, 20 of which I want to be correct. Probability of being correct is 1/4 to the 20th. And so what is this C3020? Let's see what it is as a number. 30, and then go get your C20. It's going to be huge, right? We're not even going to write it down. It is, oh boy, 30,045,015. So this is what's on my calculator. 30, 045, 045,015. That's how many different rearrangements there are of correct and wrong answers on a 30 question test. So what does that look like? What does that include, I guess? The first 30 right and the last 20 wrong, and then an intermixing of all of those. Don't write that number down. You have it parked here. I just wanted to do that. So I would do this into my calculator. 30C20 and hit equals, and we see that big number. Then immediately hit times, and then an open parenthesis. Don't skip the open parenthesis if you're using fractions. Times 1 divided by 4, close it. And then raise that to the 20th power. Then don't hit equals, just hit times. Times. And open parentheses, 3 divided by 4, close the parentheses. and then to the 10th power, and hit equals. And you're going to remember how big this number was, right? That 30 million number. When you type that all in, you're going to find the probability that you get 20 correct just by guessing, right? And you have nothing like that has, let me count the zeros. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 zeros, and a 1539, so a 154. A very, very small chance of happening. And that's because you're expecting about a quarter of the answers to be right. 30 divided by 4 is 7.5. You're way away from that 7.5 number. It's very unlikely that you're going to be able to guess and get 20 correct answers out of 30. It's more likely that you're going to be around 7 or 8. Those probabilities will be higher. They're not going to be extremely high, but they're going to be way more likely to happen than this. So that's what we're looking at. Take a look at something else. They might tell you this. An airline has a 90% on-time arrival rate. Find the probability that in the next 10 flights, at least 8 arrive on time. Okay, that's what they're going to ask, some question like that, but they're going to be folding in the at least and the at most. Now, you don't want to be triggered. In the 4.3 section, when you had an at least 1, the probability, so if you had the probability of at least 1 of those flights arriving on time, we recommended a different procedure to handle that, because to handle this directly, there would be 1 flight arriving on time, or 2 flights arriving on time, or 3 flights arriving on time, or 4 flights arriving on time, or 5, or 6, or 7, or 8, or 9, or 10. And you would have to do 10 individual calculations and then add them all up. That's a lot. The only thing not in this category of 1 flight on time, 2 flights on time, 3 flights is, and all of the others, is no flights on time. So wouldn't it have been easier, rather than to figure out 10 of these things and add them up, to figure out the opposite and subtract it from 1? Of course. Now, think about the question we have right now. Is it this big, lengthy mess? And the answer is no. So sometimes I'll get students, they don't really understand why they did the 1 minus 0. I try to, and then they'll come and I'll show them just exactly what I showed you. So remember what we want. We want at least, and I'll put it in a different color. Oops, still have the eraser. We want at least 8 arriving on time. Well, what's that? That's the probability of 8 flights arriving on time, or 9 flights arriving on time, or all 10 flights arriving on time. That's not bad. If you are determined to do a 1 minus, then you have to do 1 minus everything that's not written here, which is 0, 1, 2, 3, 4, 5, 6, and 7. Would you like to do 8 calculations, right? 1, 2, 3, 4, 5, 6, 7, 8. Add them up and subtract from 1, or would you like to do 3 calculations and add them up? Of course you'd like to do 3 calculations and add them up. So you're not going to avoid any work. There's no magic button to hit. If you need to find at least, you walk in what I call eyes wide open. You walk in with experience and you know, oh, every time it says at least, I got to do more than 1 calculation. If it says at most, it's that number and lower. And you'll have those in the homework. They won't be a big deal. Now I'm going to move these. Where? Right over here. Over to the left-hand side. So let's go find the probability of 8. How many flights are there? There's 10. And we need 8 to arrive on time. What's the probability that 1 arrives on time? 90%. 90%, this percentage that's given right up here, that is the probability of success. That's the probability of arriving on time. And so we have a 0.90 in there. How many times do we need that to happen? 8 times. Well, because not all 10 flights are arriving on time, I need some to arrive late. That probability is 1 minus the 0.90. I need that to happen twice. So they don't have to say much to give you all the information that you need. This is the probability that exactly 8 arrive on time and the other 2 are late. The probability that 9 arrive on time is C10-9. 0.90 to the 9th, 0.10 to the first power. Out of 10 flights, I need 9 to arrive on time. The probability that a single flight arrives on time is 0.90. I need that to happen 9 times. And I need the flight to arrive late once. And then there's the doing all 10 flights. And you don't really need this formula. You can just do your old 4.2 stuff. But the formula works even here, so I'll just keep it alive. Now, if you don't remember what 0.10 to the 0 is, no problem. Your calculator will do it for you. It is 1. In C of 1010, you're going to find out to be 1. So it's exactly the same thing that you were doing in 4.2. 0.9 to the 10th power is the answer to that one. But let's go calculate these. So hopefully this is making sense. If I just relook at the 8, out of 10 flights, I need 8 to arrive on time. Arriving on time has a 0.9 probability. I just said I need 8 of them. That means I need the other 2 to be late. That has a 0.10 one. So I'm just trying to say it in different ways. Calculating that first one, typing in a 10, going to get my C, typing in an 8 and hitting equals. I see the number 45 like you do, times 0.9 to the 8 times 0.1 to the second. You can put the zeros in there or not. I did something wrong. Okay, 0.9 to the 8th. Okay, I'm going to redo that because I don't know if my calculator did something weird in that process. Apologize for the time thing here. But these are good examples of what you're going to see as you navigate through the homework and the exam. Yeah, I had done it right. 0.1937. So I'm going to put 0.194. I'm just going to go out to 3 significant digits. 10C9. You run that, you'll see a 10 times 0.9 to the 9th times 0.1 to the first power. And you're going to get a 0.387. Now that one's super big and bigger than the last because that's what's most likely to happen. If the on-time arrival rate is 90%, then that's going to be the largest probability when you have 90% of your flights like we do with 9 out of 10 arriving. C of 1010 is going to be 1. 0.10 to the 0 is going to be 1. And so you just end up with 0.9 to the 10th power, as you should. And we get 0.3486. So I'll do 0.349. Now we're not done. The probability that at least 8 arrive on time is the addition of those two. So we're going to take our 0.194, add to that the 0.387, and add to that the 0.349, and we're going to get 0.93. You have a 0.93 probability that at least 8 are going to arrive on time. And that makes sense because we're right around what should happen if there truly was a 90% on-time arrival rate. So use these as an example along with the examples that are already done for you in the book as well as the ones done for you in My Math Lab. Hopefully you're using those resources and not just relying upon these videos, but I'm happy though if the videos are sufficing in order to help you understand. All right, apologize for the delay where I went and found a calculator, but thank you for your patience and I hope this is meaningful and helpful.